In December 2024, Google unveiled Willow, a quantum chip that solved a problem in 5 minutes, a problem that would take classical computers 10 septillion years. The press called it a speed record. But Google's Hartmut Nevin said something the headlines buried. He said the results lend credence to computation occurring across many parallel universes. That was not a metaphor. And when a later experiment appeared to send a signal backward through time, key scientists refused to publish. At 9 a.m. UTC on December 9, 2024, Google's Quantum AI group published a press release and blog post that sent shockwaves through the scientific world. Willow, their new quantum chip, had completed a random circuit sampling problem in just 5 minutes, a task Google said would take a classical supercomputer roughly 10 septillion years. 10 septillion years is not just larger than the age of the Earth or the Sun. It dwarfs the entire lifespan of the observable universe by a factor of 1 billion. The claim landed on the front page of the BBC and tech news feeds everywhere. Headlines spoke of a speed record, a new era for quantum hardware, and the urgency of post-quantum cryptography. But buried beneath the technical triumph was a line that most outlets skipped over. At 10:05 a.m., during a live stream summit, Hartmut Nevin, head of Google's Quantum AI group, declared, "The power we see in Willow is precisely the kind of evidence that quantum computation is exploiting many parallel universes." Nevin did not present this as metaphor. He invoked the many worlds interpretation directly, tying Willow's benchmark to a hypothesis that computation may physically unfold across parallel realities. The press release itself called Willow a major step toward a useful, large-scale quantum computer, but Nevin's statement, quoted in the Quantum Insider the next day, raised a question that mainstream coverage avoided. If Willow's result is real, what kind of world are we living in? The blog post linked to a Nature preprint detailing a 105-qubit chip, a 5x5 encoded lattice, and an error-corrected circuit depth that, according to their model, would require more computing resources than exist in the universe. The internal slide deck, later archived, set out an even more ambitious roadmap, targeting 1 million qubits by 2029. Yet the philosophical shock was immediate. Was this just a new kind of speed, or a signal that the boundaries of reality itself were being probed by a machine? The mainstream press kept the focus on cryptography and hardware, but for those following the technical language, the stakes had shifted to something far stranger. Quantum computing does not just speed up calculations, it questions the rules of reality itself. The foundation is the qubit, a unit of quantum information. While a regular bit is either 0 or 1, a qubit can be both at once, like a coin spinning in midair, not heads, not tails, but a blur of both. This is superposition, and it lets a handful of qubits represent more possibilities than any classical computer could handle. Every new qubit doubles the number of possible states. With 105 qubits, the Willow chip can explore over 4 times 10 to the 31 combinations, more than the number of atoms in the solar system. Entanglement takes things further. When qubits are entangled, a change to one instantly affects the others, even if they are light years apart. Imagine rolling 2 dice in different galaxies and always getting the same number. This is not speculation. It has been measured in labs and forms the backbone of quantum computation. David Deutsch, a leading quantum theorist, argued in 1985 that the only way to explain quantum computing's power is if calculations happen across many parallel worlds. In his view, when a quantum computer runs, it is as if countless versions of the computer in parallel realities are all working together, their results interfering to create an answer in our world. Many worlds is now the dominant model among quantum scientists. When Google's Hartmut Nevin linked Willow's results to this idea, he echoed a growing belief that quantum computation may be evidence that our universe is just one branch among many. The real question becomes, what kind of evidence could force us to accept that computation and causality might stretch beyond a single reality? On October 2, 2025, Google's Quantum AI team took the stage to demonstrate a protocol they called Quantum Echoes. The lab's white-coated researchers, gathered around Willow's cryostat, described the experiment as a stepwise dance through the fabric of time itself. The core technique, once known in physics as the out-of-time ordered correlator, was rebranded for the public as the out-of-order time correlator, an attempt perhaps to make the result sound less esoteric. But the protocol's structure remained unchanged, a sequence designed to scramble and then unscramble quantum information, as if asking the universe to replay its own memory. The procedure began with Willow's qubits cooled to near absolute zero, each one initialized in a pristine ground state. The team applied a random unitary circuit, spreading quantum information across the device in a tangle of superpositions and entanglements. At a precise moment, a single qubit was perturbed, a nudge that would ordinarily ripple outward and be lost in the chaos. But instead of letting the disturbance fade, the researchers triggered a reversal. Every quantum gate was replayed in exact reverse order, the circuit unwinding itself as if time were running backwards. What followed was the critical measurement. Using dispersive readout resonators, Willow's hardware captured the final state of every qubit, digitizing the results with an accuracy exceeding 99.5%. The team repeated the protocol tens of thousands of times, each run producing a cloud of bit strings. By comparing the probabilities, they reconstructed the out-of-order time correlator, and observable that in this context revealed something deeply unsettling. The echo of the original perturbation appeared not just after the reversal, but in some runs, before the signal could have possibly arrived by ordinary means. The data showed a pre-signal effect, a statistical bump in the correlator that classical physics cannot explain. The team's own logs and calibration files, released alongside the paper, documented every control experiment and every artifact ruled out. For the first time, a quantum processor at scale had produced evidence that information might not be bound by the familiar arrow of time. The claim was clear, the numbers precise, and the challenge to the rest of the scientific community was implicit: replicate this or explain it away. Doubts spread quickly through the quantum research community. Scott Aronson, one of the field's most respected voices, called out a fundamental problem. Without full access to Google's raw data, independent verification is currently impossible. The Willow team's headline figure, a 0.14% 2-qubit gate error, was impressive on paper, but still above the threshold most theorists consider necessary for truly fault-tolerant algorithms. For critics, this number raised more questions than it answered. Was the speed-up real, or was it an artifact of selective reporting and post-processing? The skepticism did not stop at technical details. Over a span of just a few months, 7 manuscripts challenging Willow's methodology or the multiverse framing were submitted to major journals. Every one was returned with a rejection, most within 2 weeks, a turnaround so fast that some researchers began to wonder about editorial pressure behind the scenes. In online forums and private Slack channels, the pattern became a story of its own. Was the peer review process being short-circuited? Jensen Huang, CEO of NVIDIA, added fuel to the debate. In a high-profile keynote, he projected that practical, fault-tolerant quantum computers were still a decade away at best. His forecast clashed directly with Google's roadmap, which promised usable, error-corrected quantum algorithms within just a few years. The rift between industry giants exposed a deeper uncertainty, even among leaders in quantum hardware and AI. There was no consensus on how close the world truly stood to a quantum revolution. As doubts mounted, the stakes only grew. Was Willow a genuine leap, or a case of scientific overreach protected by corporate secrecy? The refusal to share data, the rapid-fire rejections, and the conflicting public roadmaps all fed a sense of controversy that refused to die down. On March 28, 2026, Google opened the Willow Early Access Program to outside researchers, but the invitation came with conditions that raised immediate questions about transparency. Only select academic and industry labs could apply, and every participant had to agree to a standard acknowledgement, crediting Google's infrastructure in any resulting publication. The eligibility rules went further. No team with an existing contract from a competing quantum vendor could participate, and the program explicitly excluded major U.S. government agencies. The Department of Energy, National Science Foundation, and even DARPA were all deemed ineligible for the first round, with Google citing export control concerns as the reason. When the first cohort was notified on April 15th, the list included a handful of prominent universities and private labs, but no federal science institutions. Access to Willow's hardware was not just a technical privilege. It became a tightly controlled asset, shaping who could verify, question, or even witness the most consequential results in quantum computing. This structure, more than any technical barrier, set the boundaries for what could be independently confirmed and what remained locked behind Google's walls. The Nature paper on Willow's quantum echoes drew more than 100 co-authors from Google, Stanford, and MIT, but the real test was always outside the company's walls. In 2026, UC Berkeley's joint experiment with Google confirmed Willow's error reduction curve, but no one else matched the full 13,000-fold speedup. The stakes sharpened as China's Hefei lab announced a portable 105-qubit prototype, aiming to replicate the out-of-order time correlator results. Google's internal roadmap now pointed to a 200 logical qubit milestone by the end of the year, while rival teams in Europe and Asia raced to catch up. The world's most powerful quantum hardware had become a new front in a global contest, where the difference between confirmation and doubt could redraw the boundaries of science and national security. Today, Google's results remain locked behind proprietary walls. Hartmut-Nevin's claim that quantum computation occurs in many parallel universes was not a metaphor. Scott Aronson warns that outsiders cannot verify the work, and out-of-order time correlator data remains unpublished. If reality is stranger than science admits, who controls the truth? Share your thoughts below.